time.
It's the one thing we're all trapped in, constantly rushing forward at exactly 1 second per second. But what if we could break the cage? What if the past isn't gone and the future is already written? Today, we aren't talking about DeLorean cars or blue police boxes. We are looking at the brutal, unyielding laws of physics. Over the next hour, we will explore how you can technically travel to the future today, why the past is fiercely protected by the universe, and the mind-breaking paradoxes that could destroy reality itself. Grab your gear. We're going deep. To understand how to break time, we first have to understand what it actually is. For centuries, Sir Isaac Newton's view dominated science. Time was an absolute, universal clock ticking away at the exact same rate for everyone, everywhere. But in 1905, a young patent clerk named Albert Einstein shattered that idea forever with his special theory of relativity. Einstein realized that time is not absolute. Instead, it is deeply woven together with the three dimensions of space into a four-dimensional fabric called spacetime. Even more shocking, Einstein discovered that your speed through space directly affects your speed through time. This is called velocity time dilation. Think of it this way. The universe has a strict cosmic speed limit, which is the speed of light, roughly 300,000 kilometers per second. Everything in the universe moves through space-time at a combined, constant speed. If you are sitting completely still, you are moving through space at 0 miles per hour, which means all of your motion is directed through time. You are moving forward into the future at a normal, standard rate. But the moment you start moving through space, you have to divert some of your motion away from time to power your physical movement. As a result, your personal clock begins to tick slower relative to someone who is staying still. The faster you move through space, the slower you move through time. To calculate this precisely, physicists use Einstein's time dilation formula, which shows that as your velocity approaches the speed of light, the denominator of the equation approaches zero, causing time for you to stretch out toward infinity. This leads to the famous thought experiment known as the twin paradox. Imagine two identical twins. One stays on Earth, while the other boards a rocket ship capable of traveling at 99% the speed of light. The traveling twin blasts off into space, travels for what feels like just a few years to them, and then returns to Earth. When they step off the ship, they discover something mind-blowing. While they have only aged, say, 5 years, their twin back on Earth has aged decades, growing old and gray. The traveling twin has literally leaped into Earth's future. If you think this is just a wild theoretical concept, you'd be wrong. This isn't science fiction. It is a proven, measurable reality. Astronauts on the International Space Station are literal time travelers. Because the station orbits Earth at a blistering 28,000 kilometers per hour, the astronauts on board are moving through space much faster than we are. When they return from a 6-month mission, they have aged a fraction of a second less than everyone left behind on the surface. They have returned a tiny fraction of a second into Earth's future. Even the GPS satellites orbiting our planet have to be programmed with Einstein's equations built into their software. Because they are moving so fast, their internal atomic clocks gain about 7 microseconds every single day compared to clocks on the ground. If scientists didn't manually correct for this time dilation, your phone's navigation system would lose its accuracy within hours, placing you miles away from where you actually are. Velocity is our very first cheat code for time travel. But speed isn't the only way to bend the cosmic clock. In 1915, Einstein expanded his ideas into general relativity, introducing a second cheat code: gravity. Einstein realized that gravity isn't just a mysterious invisible pulling force between objects. It is actually the geometric warping of space-time caused by mass and energy. Imagine a heavy bowling ball sitting on a trampoline. It creates a deep dip in the fabric. If you roll a marble nearby, it rolls toward the bowling ball not because of a magical force, but because it is following the curved path of a trampoline. In the real universe, massive objects like planets, stars, and black holes warp space-time in exactly the same way. And because space and time are fundamentally linked, warping space means you also warp time. This is known as gravitational time dilation. The closer you are to a massive object with intense gravity, the more space-time is compressed, and the slower your clock ticks relative to someone far away in empty space. To see this in action on a cosmic scale, we have to look at the most extreme gravity wells in the known universe: black holes. Imagine a highly advanced spaceship flying to Sagittarius A*, the supermassive black hole at the center of our galaxy. This black hole packs the mass of over 4 million suns into a terrifyingly dense point. If our astronauts park their spaceship just outside the event horizon, the point of no return, and orbit there safely, they enter a zone of extreme time dilation. The immense gravitational field slows their time down to an absolute crawl. For the astronauts on board, a few hours might pass as they look out at the swirling, glowing accretion disk. But back on Earth, away from that massive gravitational warping, decades or even centuries would fly by. If those astronauts were to fly away from the black hole and return to Earth, they would find themselves stepping into a distant, future human civilization. They would become relics of the past. But gravity comes with a terrifying catch. It is a strict, one-way ticket. If your spaceship slips just a fraction too close and crosses past the event horizon, the physics inside changes completely. Inside a black hole, the dimensions of space and time actually swap roles. Moving forward in time becomes as physically unavoidable as moving forward in space. You don't just get trapped in a dangerous location, you get permanently trapped in the future, with no possible way to ever turn back. This brings us to the ultimate question that has haunted physicists for generations. If traveling to the future is an established, proven fact of physics, is it possible to go backward? Can we travel to the past? To achieve backward time travel, the laws of physics require us to create what is known as a closed time-like curve, or a CTC. In simple terms, a closed time-like curve is a path through space-time that loops back on itself. If an object travels along this path, it moves forward through its own local time, but because the fabric of space itself is so radically twisted, the path eventually ends up back at the exact time and place where the journey started. For decades, scientists have looked for theoretical workarounds in general relativity that could allow for these loops. The most famous candidate is an Einstein-Rosen bridge, commonly known as a wormhole. In theory, a wormhole is a shortcut through the fabric of the universe, connecting two completely different points in space and time. Imagine folding a flat piece of paper in half and punching a hole through it with a pencil. Instead of traveling all the way across the surface of the paper, you can just step through the hole, instantly crossing light years of distance. In the late 1980s, legendary physicist Kip Thorne realized that a wormhole could potentially be turned into a backward time machine using a combination of gravity and velocity. Imagine you have a stable wormhole with two openings or mouths. You keep mouth A sitting completely still in your laboratory on Earth. You place mouth B inside a highly advanced spaceship and accelerate it across the cosmos at nearly the speed of light, exploiting the velocity time dilation we talked about earlier. After a long journey, you bring mouth B back to Earth. Because of time dilation, mouth B is now significantly younger than mouth A. The two ends of the wormhole are now operating on completely different times. If you step into mouth A in the future, you would instantly travel through the throat of the wormhole and exit mouth B in the past. It sounds mathematically perfect on paper, but the real universe presents a massive, destructive problem. First of all, to even keep a wormhole open, you would need a hypothetical form of matter known as exotic matter, which possesses negative mass and negative energy pressure to counteract the intense gravitational urge of the wormhole to instantly collapse. Second, the moment you attempt to align the two mouths of a wormhole to create a past travel loop, quantum particles and vacuum fluctuations would begin to enter the wormhole, travel back in time, exit the other side, and enter it again. This would create an instantaneous, infinite feedback loop of energy, very much like placing a live microphone right next to a speaker, causing a deafening, piercing screech. This runaway quantum feedback loop would release such a cataclysmic burst of energy that it would almost certainly vaporize the wormhole instantly, long before a human could ever attempt to step through it. Because of these extreme physical barriers, the late Stephen Hawking proposed a theory called the chronology protection conjecture. Hawking argued that the fundamental laws of physics actively conspire together to prevent closed time-like curves from ever forming, effectively protecting history from time travelers and keeping the universe safe from total causal collapse. And the universe has a very good reason to protect history, because backward time travel introduces logical nightmares that threaten to rip reality apart at the seams. These are known as causality paradoxes. The most famous of these is the grandfather paradox. Imagine you build a fully functioning time machine, step inside, and travel back to the year 1950. While exploring the past, you encounter your own grandfather as a young man, and through a tragic accident, you cause his untimely death before he ever meets your grandmother. Think about the logical chain reaction this triggers. If your grandfather died in 1950, your parents were never conceived. If your parents were never conceived, you were never born. But if you were never born, you never existed to grow up, build a time machine, and travel back to 1950 to cause the accident in the first place. Therefore, your grandfather lives, meaning you are born, meaning you do go back, and eliminate him. The timeline locks itself into a broken, impossible loop of cause and effect where reality cannot resolve itself. An equally disturbing puzzle is the bootstrap paradox, which deals not with objects, but with information. Imagine a time traveler who packs a pristine copy of Albert Einstein's 1915 paper on general relativity into their backpack. They travel back to the year 1905, track down a young, struggling Einstein, and hand him the completed paper. Einstein looks it over, copies it word for word, and publishes it to global acclaim. Now, ask yourself, who actually came up with the theory of relativity? It wasn't the young Einstein because he just copied it from the book. But it wasn't the time traveler either because they just found the book in a store in the future, written by Einstein. The information has no true origin point. It was bootstrapped directly into existence out of absolutely nothing, violating the fundamental law that everything in our universe must have a definitive cause. Faced with these mind-bending paradoxes, some physicists turned to the wild world of quantum mechanics for a possible escape hatch. Enter Hugh Everett's many worlds interpretation. In the quantum realm, particles don't exist in just one definite state. They exist in a cloud of probabilities called a superposition, occupying multiple possibilities at the exact same time. The many worlds interpretation suggests that the universe doesn't choose just one outcome. Instead, every time a quantum event occurs, reality literally fractures, splitting the universe into an infinite tree of parallel, branching timelines. If this quantum interpretation is correct, it completely solves all time travel paradoxes. If you travel backward in time and accidentally prevent your grandfather from meeting your grandmother, you are not actually changing your own personal past. Instead, the moment your time machine materializes in the year 1950, you have stepped onto a completely brand new, parallel branch of the multiverse. In this new timeline, you will never be born, but your original home timeline, the one where you grew up, built the time machine, and left from, remains completely untouched and safe. You haven't erased your existence. You have simply moved laterally into an alternate reality. Other scientists look to the concept of quantum entanglement, where two particles become deeply linked across space and time. Recent laboratory experiments have shown that we can simulate quantum particles interacting with past versions of themselves, changing their states in ways that mimic backward time travel on a subatomic level, all without triggering any destructive paradoxes. But while a single subatomic photon might be able to cheat the timeline through quantum loopholes, scaling that up to a macroscopic human being made of trillions of atoms is an entirely different story. So, where does that leave us at the end of our journey? Is time travel truly possible? To the future? Absolutely, without a shadow of a doubt. We are all time travelers moving forward right now, and with a fast enough spaceship or a strong enough gravitational field, we could easily vault ourselves forward by centuries to see the end of human history. But the past? The past remains a locked vault, fiercely guarded by the fundamental laws of quantum physics, thermodynamics, and the strict rules of cause and effect. Perhaps that is exactly how it should be. The universe protects its history so that our present choices actually mean something, ensuring that the timeline we build today cannot be unwritten tomorrow. If you enjoyed this deep dive into the cosmic fabric, make sure to hit that subscribe button for Scientific Spectrum. Leave a comment below. If you could travel to any point in time, forward or backward, where would you go? Until next time, keep looking at the stars.